Welcome, ladies and gentlemen, to this video lecture. Let's take a look at this problem. This is exercise 3.2, page 161, number 3. And this exercise says, let f and g be functions from R to R, a, L, and m be real numbers, and we assume the following. So the limit as x tends to a of f of x is equal to L. The limit as x tends to a of g of x is equal to m, and L is less than m. Then the question asks to prove that there exists a delta greater than 0, so that for all x in the domain of the functions, if this x is close to a, within a delta distance of a, then f of x is less than g of x. Okay. So what do we have to do? We have to somehow construct such a delta which does that. And how will we do that? We will use our definitions. Okay, so before we start, let us just get an intuitive picture of what is going on here. We've got our value m and L over here, and a over there, and the limit of f is L, limit of g is m. So first of all, so let's say g looks like that, and let's say f looks like that. Okay, so if this is f and that is g, let us just get an idea of what we can do. Let us look at our assumptions. So the limit as x tends to a of f is equal to L. So f, I've drawn or depicted in this as this green line. The graph of f I have depicted as this green line. So that this limit is equal to L, that gives us information. That tells us for every epsilon there exists a delta, so that if x is within a delta distance of a, then the function value is within a an epsilon distance of L. And that works for every epsilon. Since it is an assumption, we can bring any epsilon and we can obtain a delta that works with that epsilon. So why don't we cut this interval in half? This interval from L to M. Let's cut it in half. And if we consider this interval around L, we can buy a delta so that our function always lives, or the points on the graph of our function, if we are close enough to a within a delta distance, we can force our function to live or to have its function values in this interval around L. So we can buy a delta so that we are close to L, or within this distance of L. So we can find an interval so that if we are close to A, or in other words, in this interval around A, then the function values lie within this red interval around L. Okay, and that is how we will use our definition. And similarly, again, let us cut this interval in half. We do the same thing for G. So we take an interval around M with this radius, and then this assumption says that there exists a delta, so that if we are within a delta distance of A, then our function values for G all lie within now this interval around M. Okay, so that is how we will use our definition for G. And in the end, we will take the smallest of the two intervals because we want F to be below this red line, and we want G to be above this red line at the same time. So we will take the smallest of the intervals that we obtain around A. Okay. And to be able to obtain these intervals around A, we need to know what this distance is. So this distance is halfway between M and L. So M minus L, that is this whole distance, and halfway is M minus L over 2. So this will be the epsilon that we will use to buy our deltas here. Okay, so that is our plan. So let us write out our plan. So let us first write out exactly our assumptions. So we assume that the limit as x tends to A of f of x is equal to L. This means something very specific. This means for every epsilon greater than 0, there exists a delta greater than 0, so that for all x in the domain of the function, if x is within a delta distance of A, but not equal to A, then the function value f of x is close to L, or in other words, within a delta, an epsilon distance of L. And this is an assumption, so this is a shop. If we pay with an epsilon, we can get a delta out. And also, we assume that the limit as x tends to A of g of x is equal to m. This means the following: for every epsilon greater than 0, there exists a delta greater than 0, so that for all x in the domain of the function, if x is within a delta distance of A, then g of x is within an epsilon distance of m. And again, this is an assumption, so this is a shop. If we pay with an epsilon, we can get a delta out. Okay, and what do we have to prove? We have to somehow define a delta. So let us define a delta. We don't know how to define our delta yet. And what does this delta have to do? What are we trying to prove? So we have to show that such a delta exists, so we must define it so that for every x, so take any take any x in R and assume that this x is within this delta distance of A. And now remember, where do we want to get? We want to show f of x is less than g of x. Okay. And what are we going to do? Well, we're going to cut this interval in half. And we've already seen, well, what is halfway? Halfway is m minus L. So let us define d to be m minus L over 2. And that is a positive number. And now we're going to use this positive number to pay for deltas at the shop. So let us call this assumption A and that assumption B. So using D for epsilon in A, what happens? Well, we're taking this D, we're paying with D, and we're getting a delta out. So let's put a different sticker on this delta. There exists a delta 1 greater than 0. So that if 0 is less than absolute value of x minus a, less than delta 1, then f of x minus L is less than d, because we paid with d. And since we paid with d, the delta that we get out works with that d. And now we're going to do the same with b. So using the same d for epsilon in b. So now we're paying with d here, and we're getting an epsilon out. And we'll put a different sticker on this delta. Did I say epsilon? I meant delta. We're paying with d, we get a delta out. And let's put a different sticker on this delta. So there exists a delta 2 greater than 0, so that if 0 is less than absolute value of x minus a, less than delta 2, then g of x minus m is less than d. Okay, so now we have these deltas to work with. We have delta 1 and we have delta 2. Okay, so we want here, under this assumption, we want delta to be less than delta 1 and to be less than delta 2, because if we can force that, then we obtain the conclusions here, that absolute value of f minus L is less than d, similarly for absolute value of g minus m. So we want this delta that we are constructing to be less than delta 1 and delta 2 at the same time. So what we will do is we will take the minimum of delta 1 and delta 2. And then what happens? So here, and then we have x minus a is less than delta, but delta is the minimum of delta 1 and delta 2, so it is less than delta 1 specifically, and similarly less than delta 2. So, and therefore, we now have both of these hypotheses satisfied. So for this x that we took, both of the above hypotheses are satisfied. So therefore, we obtain that the conclusions are true. So therefore, we have f of x minus L is less than D, and g of x minus M is less than D. And remember, where are we trying to get? We are trying to get, we're trying to show that f of x is less than g of x. Okay, and what we will do now is we will just do a little bit of algebra and expand these two inequalities and obtain the conclusion that we're looking for. So we're trying to show that f of x is less than g of x. So let us do that. So if the absolute value of fx minus L is less than D, then fx minus L is between minus D and D. And let us add an L everywhere, so L minus D, D plus L. And remember, where are we trying to get? F of x should be less than g. So in fact, we only need the right-hand side here. So let us write out the definition of D, m minus L over 2 plus L. And let us simplify that. That becomes, that's going to be 2L over 2. And we're subtracting one of the L's, so that becomes m plus L over 2. So let us write it this way. F of x is less than m plus L over 2. And notice here, this is not a surprise. That is exactly how we constructed our D. We expect on this interval that x lives in is that f of x is halfway between m and L, or is less than halfway between m and L. Okay, and now let's do the other side for g. So g of x minus m is between minus d and d, and let us add an m everywhere, so this m minus d is less than g of x less than d plus m. And in fact, we only need the left-hand side here. G of x is greater than m minus m minus L over 2. And if we simplify that, we see that g of x is greater than m plus L over 2. So remember the brackets there. It's minus L plus L. So 2m minus m is m. Minus minus L is plus L. And this is also not a surprise. This is how we defined our D. We expect our function values for g to be above halfway. So here, this red line is halfway between m and L, and we expect, by how we've chosen our D. So this is our D. So this distance is D, and that distance is D. So we expect our function values to be above this red line, close to A. So that is not unexpected. And now putting it together, hence, what do we have? F of x is m plus L over 2, less than m plus L over 2, and g of x is greater than m plus L over 2. So f of x is less than g of x. Okay, and here is our proof finished. So let us go, just go through our proof again. So we defined our D. We used our D to buy our deltas. We took the minimum of the two deltas, and now we showed that if x, so any x, and now this x is the same x everywhere. If that x satisfies the condition of being within a delta distance of a, which delta? This one. So this x, we assume that this x satisfies that condition, and by how we've constructed our delta, delta is less than delta 1, delta is less than delta 2. So this x that we've taken under this assumption is within a delta 1 distance of a and is within a delta 2 distance of a. And now, because of how we've constructed this delta 1 and delta 2, we are now in the situation where the hypothesis of these implications are true. So we obtain the conclusions. So that is how we get these two conclusions. And once we have these two conclusions, the rest is just algebra. So we expand our inequality for f. We show that f of x is less than halfway between m and l. So m plus l over 2, the average of m and l, that is exactly halfway. If we go back to our drawing, our f close to a has to be below halfway. And similarly for g, our g has to be above halfway. And now putting it together, we see that f is less than g. Okay, and that is it for this exercise. I will see you in the next one.